Hello everyone. I'm Łukasz Borowiecki. I'll be talking about Shapley values and explainability. It won't be around LLMs, so no language models mentioned. So I assume if you're not interested, then it's okay. Okay, so I'm Łukasz Borowiecki. I'm the head of 10 Senses, where we basically do data, algorithms, stuff like that. I have a few affiliations. I'm the member of the AI working group at the Ministry of Digitization, where we focus on consulting around Polish AI strategy. I'm a member of DAMA Poland, so Data Management Association, where we focus on data quality standards and data management. My background is in social sciences, so I'm a sociologist. I did my PhD in econometrics, so I'm this type of guy who basically is skilled in analytics. Okay, so we have AI Act coming. It's supposedly, put in force finally by September 2026. It seems that it will be postponed by 1.5 years till December 27 with this digital omnibus from EU. And explainability is a part of it because AI Act is built around these layers of risk. So we are interested in the third layer, high risk, which is regulated. And it's around these use cases where AI can do harm. So where there's credit scoring, profiling for recruitment process, biometric identification. So any case where the decision by AI can, affect the welfare or health of a person. And there are quite a few requirements around it. So, for example, in Article 10, we see that in order to check whether there is no bias in an AI system, we are actually capable, we are allowed to withhold GDPR and analyze sensitive data. So that's, like a big thing. In Article 13, we see that there is the mentioning of transparency so that the people who coordinate and work with AI systems should be able to interpret what is the outcome of the AI system and why was the decision made. In Article 14, we see this mentioning of this tendency to automatically rely on the output which may be biased. Also in Article 30, we see that workers who work with AI systems should be able to interpret how decision is made. In Article 86, we see that for individual clients, they have the right to get the explanation how the AI system came up with the decision. So it doesn't work with companies. It's only for people, for humans. But for high-risk systems, they can ask for explanation. And when we go to annexes of AI Act, we see that in the documentation part, the documentation of AI system of high-risk AI system should have the human oversight in it. And also there is this mentioning of Article 21, where this explainability should be also there should be an ability to show it to regulators. So we see that we need explainability for high-risk systems, where in order to show the client how the decision was made, for the managers so that they can manage the AI system properly, but also for authorities. So explainability has three end users. And this is something which was killed. There was this, but it will resurface in one way or the other. there was this idea to make AI Liability Directive, which addresses the thing like what happens if there is damage, who is liable. And because big companies have this muscle, they are huge, and individual clients cannot actually, like go to court against big companies. So there was this idea that if there is damage, if the damage was because of the of IT system and AI was there, the companies assumed to be liable, and it should explain that it did no harm. So the the proof is on the company. So it didn't go into place. So we don't have this instant regulation. It was killed, but sooner or later, in one way or the other, we'll see it, because like there will be cases in courts, and there needs to be regulation about it. Okay, so what is explainability? Depending on the algorithm, we will have different techniques for explainability, and even here you see that it's like, even visually, these are different techniques. So there is no one explainability. However, for tabular data, so say CRMs, patient data, anything that is in form of the table where we use machine learning there, we have Shapley values which are popular. And explainability is something different than transparency and no discrimination. So transparency is the thing that we can look at all the parts and how the data move around through the elements of the algorithm. Explainability is more about causality and how the process works. But even these two don't give us the assurance that there is no discrimination, because machine learning models are built on data from real world, and there is bias, like our world is not perfect. So there is always bias in the data, and it's for this reason it's impossible to distinguish between bias and actually proper functioning of the algorithm. Okay, let's think about a CRM application. So we have a CRM and a company, and we use it for lead scoring, to profile potential clients. For customer segmentation, we may use it for churn prediction to find out those who are probable to leave our company, like clients who don't want our services anymore. And these type of, I will be talking about CRMs, but these types of techniques can be also used for patient data, for price estimation, for stock data. And when we think about this problem of black box, is that it's not that we don't understand what is happening in our machine learning model. It's just that there are so many moving parts, so many elements, that it's impossible to trace how information, moved through the whole process, because like there are so many elements. For this reason, we call them black box. And we don't have a simple solution to present the logic. It's just too complex, but we can estimate it. And a practical use case, say it's 2030 and all the regulations are in place. There is a lawsuit. So an NGO sues a big financial institution saying, your institution basically discriminates our clients. So everyone is getting discounts. You are famous for discounts. However, our clients never get discounts because there are women with children, or they are elderly, or they are handicapped. So they never get discounts because of these, vulnerable features. You discriminate financially against them, and you will have to pay. And the financial institution says, no. It's the other thing, like it's other demographics, like it's true they don't get discounts, but it's because of other demographics, or it's because of a different history of using financial services. So it's because of that. And the court says, show me how the AI system made its decision. And for this, we need reporting of machine learning decisions by machine learning. We need explainability. And let's think about this person. So we see the demographics, we see his or her credit history, some other information about using financial services. And the algorithm predicts that it's 9% of probability that the person will not repay at least once in more than 90 days. That's the risk. With Shapley values, we can get that. So we can we can measure what's the impact of each of these demographics or features of the person. So in this case, we see that the demographics didn't impact much. Also, the credit history didn't impact much. Both helped a bit, like lowered the risk. But there are two features which according to the algorithms, are highly risky. So there is this high revolving utilization of unsecured lines, and there is open loans and lines of credit. So these two features make this person risky. And in this particular case, the financial institution could say, it's not because of the demographics. It's because how he or her used the financial services in the past. And how it works. So we bombard the algorithm with questions. So we permutate the data. So if for the first time it was 9%, then what if we put the same data into the algorithm, but we tweak the age? We make him older. What would be the outcome? What if we ask the algorithm once again and made the income lower? What if we ask the algorithm once again and change something, made the data so that he has one person who relies on him in the family? So we constantly ask the algorithm and we measure differences so that we can estimate what's the impact of each variable. And when we compare two persons, so we have who are some ways similar, but one is much riskier. We see both are 57 years old. They don't have dependent family members. The other guy earns significantly less. Once in the past, he did not repay on time. They differ in debt ratio and open lines of credit also. So how do they compare? And when we compare them, we see that according to the algorithm, the change in monthly income is not that relevant. However, the fact that once he did not repay on time is a risk factor, and it boosts the risk for the person. Also, this revolving utilization of unsecured lines for this second person is also more important, and the debt ratio is important. So we can compare similar people to check, not only show that one person we have the outcome for one person, but we can benchmark it to say other people who are similar or for other groups. And practical application. So we can check whether the model treats a person differently from, say, his or her age group. We can quantify these differences in numbers, and we can even do some specific calculations, because if we have these demographics and features of a person, we can estimate probabilities, and we can assign money to these probabilities. We can make various calculations, even in Excel, around how much money would it potentially cost, or how much financial risk do we put when we provide services for a group or another. We can use it for direct marketing. So we can check what's the, say, net effect of a marketing campaign, and not only the total net effect, but also for separate people or for separate groups. So in this case, say they're risky, so we want to call them or contact them saying that you should repay on time. And if we add historical information about the success of these companies and rebuild the model, then the machine learning model, then we can have these predictions of how various campaigns would affect, how effective they would be for these people. And in this hypothetical case, we see that for the first person, both email and phone call would work. For the second person, only phone calls work. And so it's we can use it for CRMs. We can use it for compliance with regulations. When there is black box models in fraud detection and we want to know what affected the prediction of the model, we can also use the same techniques. And also asset pricing, say we have a model which estimates prices of houses. With Shapley values, we can decompose this estimation and check, say, what's the impact of house size in specific locations, or standard of a home in various locations, because it may have a different impact in the city center and on the outskirts of the city. This one I would skip. And for those of you who think of maybe emerging a bit more into Shapley values, let me just show you what is potentially possible. Because currently that's the stage where we are at. So AI people would use Shapley values for verifying which variables have impact on a machine learning model, so that those which are irrelevant, they can throw them away, or for these capturing this individual effect for one specific prediction. However, it can also be used as a kind of regression. And if you think about it, like we had 2000, Heckman and McFadden got their Nobel Prize for sample bias and for discrete choice. We recently had a Nobel Prize for instrumental variables. And once this is properly written down with formal, formal corpus and formal papers, sooner or later there will be a Nobel Prize for using Shapley values in economics. It's just like it's there in the future. Because if you think about it, when we use regression, we usually just say we estimate a wealth of a person, and we put what's the years of education, what's the age, what's the gender, etc. And this allowed us to predict the income. And regression is great because it makes a representation of the world. It gives us parameters which capture the effect of each variable, and also gives us estimation of error. With machine learning, we only get the first one, so the prediction. Machine learning is great at representing the world, but it's only that. However, it's better than regression because in regression, there's assumption that, if you use regression, a male from a rural place will have the same effect than the same male living in a big city. So there is always the assumption that being a male has the same effect. With machine learning, we can capture the interactions, and machine learning is good at capturing what's the impact of being a male given other variables. So it's great because it captures interactions. But then if we add Shapley values, we can estimate parameters. So we are very close to making a regression out of Shapley values. And in practical terms, like say we are estimating this income of a person, we put age of education, we put gender, then we put what's the age of a person, and the model improves. Then we add, say, sector in which the person is working, some other variables, and the model improves all the time. The problem is that in social sciences, everything is interrelated. So the more variables we add, the worse the parameters get. Because of that, we cannot add too many of these variables, and we have these confounders who just aren't there, cannot be put into model. So with regression, we always have this limited number of variables, and whatever we put into model, whether we remove our variable or add, all the parameters change. So that's a problem. But with Shapley values, we can train the model on the whole data and then use Shapley values just to estimate parameters for each variable. And with this, we reduce the problem of this collinearity because the interactions are checked. We use all variables, so confounding is reduced. We estimate only once, so we don't have the problem of variables impacting the model specification impacting the measurement. And we go beyond ceteris paribus, meaning that we have a model where being a male in a rural area and a city have the same parameter. With Shapley values, we'll have always the context. The estimation always takes the context into account. And this is like a great field. It has many applications, and like AI Act will enforce it to companies. However, if we want to put it in as a regression, we just need more work in terms of writing down all the assumptions and making it more like a regression. So that would be all. I thought it would take longer. I'm aware that like the last part may be a bit theoretical, but these are real use cases. If any of you have questions around either these AI Act cases or estimating Shapley values or this regression part, I will be there in the Q&A corner and can answer any questions. Thank you very much.